Scientists say Alaska's 1,578-foot wave missed the tour boats. Here's how close it came. 5:26 in the morning, August 10th, 2025. Southeast Alaska. Rain coming down sideways over a narrow fjord called Tracy Arm, 80 miles south of Juneau. A slab of mountainside the size of 600 football fields lets go above the toe of South Sawyer Glacier and drops straight into deep water. In the seconds that follow, the fjord throws a wall of water higher than any building on the west coast, 1.5 Eiffel Towers stacked up the opposite rock face. Here's the detail that should stop you cold. 24 hours earlier, cruise ships had been anchored in that exact spot. A National Geographic vessel was still in the wider waters nearby, close enough to feel the current shove the hull and watch white water climbing the cliffs. Had that mountain let go 8 hours later in daylight, with tour boats parked at the glacier's base the way they are every single day of the summer, this would not be a story about a lucky escape. It would be the worst maritime disaster in Alaska's history. That is not dramatic license. That is what the scientists who flew over the wreckage 3 days later concluded themselves in a study published in the journal Science. So let's get into exactly what happened, how close it came, and why Alaska's fjords are getting more dangerous every year, whether anybody's watching them or not. Start with the geography, because it explains everything that follows. A fjord is a drowned glacial valley. Thousands of years ago, a river of ice carved a trench through solid rock with walls that go almost straight up. When the glacier retreated, the ocean flooded in behind it. What's left is a corridor of water hemmed in by granite on both sides, sometimes less than a mile wide, with depths plunging hundreds of feet just yards from shore. No beach, no shallow shelf to slow anything down. Structurally, it is the worst possible container for something to fall into. Tracy Arm is one of the most photographed of these corridors in the world, a 30-mile slot canyon of water that funnels tourists past waterfalls, floating ice, and 2 tidewater glaciers, North and South Sawyer. Roughly 1.6 million people took an Alaska cruise in the year before the landslide, and a huge share of those itineraries built in a stop at exactly this kind of place. Sail in slow, get close to the ice, hold position for the photographs, sail back out. It is the postcard moment people pay thousands of dollars for. At the head of that fjord, above where South Sawyer Glacier meets the water, a mass of rock roughly 1,000 meters long and 600 meters wide had been sitting on a slope that was no longer supported the way it used to be. The glacier beneath it had been thinning for years, and as the ice pulled back, it stopped doing the one job that had kept that rock face upright for millennia, leaning against it, holding it in place. Somewhere around 5:26 that Sunday morning, that support finally gave out completely, and something like 64 million cubic meters of rock, by some estimates closer to 100 million, sheared off the mountain and fell into the fjord in a single catastrophic mass. To put 64 million cubic meters in terms that mean something, that is enough material to bury a football field under a stack of rock nearly 7 miles high. Some researchers have put the volume even higher, describing it as more than 20 times the volume of the Great Pyramid of Giza, landing in the water in one continuous slide. The impact did 2 things almost simultaneously. It generated an initial braking wave at the point of impact that reached roughly 328 feet, 100 meters, moving across the water at speeds researchers clocked above 70 meters per second, faster than a car on a freeway. And because that energy had nowhere to spread out sideways in a corridor that narrow, it had only one place left to go, which was up. The wave slammed into the fjord wall directly across from the slide and climbed it. When the U.S. Geological Survey flew a reconnaissance mission 3 days later on August 13th, geophysicists Cyrus Redd and John Lyons used GPS units and altimeters from a small aircraft to measure exactly how far up that opposite slope the water had scoured the vegetation away. Their number, confirmed later by the peer-reviewed study, came out to between 470 and 500 meters. Call it 1,578 feet at the peak measurement. Some of the earliest field estimates from the scientists on the ground ran even a touch higher, north of 1,600 feet, before the final modeling settled the figure. Whatever the exact number, it made this the second highest tsunami run-up ever measured anywhere on the planet, in the entire recorded history of instrumented science. Only one event has ever beaten it, and we'll get to that one in a minute, because the comparison is the whole reason this story matters. Farther down the fjord, at a small landmass called Sawyer Island, the wave had dropped to somewhere around 100 feet, still enough to strip the island almost completely bare of trees. Researchers who examined it afterward said Sawyer Island came out looking scoured down to bedrock, with just a couple of trees left standing where a forest had been the week before. By the time the tsunami's ripple effect traveled the roughly 80 miles out to open water and registered on the NOAA tide gauge in Juneau, it measured 36 centimeters, about 14 inches, a bump that most people on a dock wouldn't even notice. That collapse in scale from a wave nearly a third of a mile tall at the source to little more than a foot high 80 miles away, tells you everything about how these events behave. They are savagely, catastrophically violent in the fjord itself, and they burn out almost as fast as they start once they hit open water, which means the entire danger zone for an event like this is concentrated in exactly the place tour operators like to linger the longest. Now here is where the story gets uncomfortable, because this was not an empty fjord that morning. There were people inside it. A group of kayakers had made camp on Harbor Island near the mouth of Tracy Arm and reported afterward that the wave came through their campsite and swept their gear into the water while they scrambled for higher ground. They were not injured, but they were there, on the water, when a nearly 500-meter wave tore through the corridor they were sleeping in. Farther out, a National Geographic Venture cruise ship moving slowly toward the glacier was roughly 15 miles from the landslide when it happened. Passengers and crew reported feeling strong currents pull at the vessel and watched white water washing unusually high up the surrounding cliff walls, without at first understanding what had caused it. 15 miles is not close in absolute terms, but for a tsunami event, 15 miles from the source is well within the zone where a slower moving or closer anchored vessel could have been in real trouble. And this is the number that should actually make your stomach drop. Study co-author U.S.G.S, a seismologist with the University of Alaska Fairbanks Alaska Earthquake Center, said publicly after the paper came out that researchers counted multiple cruise ships in the immediate area the day before the landslide let go, not the week before, the day before. Tracy Arm is a routine stop visited by roughly 20 cruise ships and hundreds of thousands of boat-based tourists across a single summer season, along with countless kayakers, small tour operators, and private vessels. If that slope had failed 8, 10, 12 hours later than it did, in full daylight, on a Sunday in the middle of the summer cruise season, with boats holding position near the glacier, faced the way they do every single clear day, the outcome would not have been a story about swept-away camping gear. Karasozen put it about as bluntly as a scientist ever puts anything in print. "It was a close call," she said. "We dodged a bullet here." Dan Sugar, a geomorphologist at the University of Calgary and the lead author of the study, went even further, saying the timing was, in his words, unbelievably lucky, and adding a warning that should sit with anyone who has an Alaska cruise booked: there will be a next time, and next time we may not be so lucky. Nobody had this slope under watch. There was no instrument bolted to that mountainside, no satellite alert flashing on anyone's screen. The way scientists first learned anything had happened at all was secondhand, through seismographs. The Alaska Earthquake Center picked up a strange, drawn-out signal around 5:30 that morning, a rumble that built and faded instead of cracking sharply the way an earthquake does, which is the seismic signature of a landslide rather than a fault rupture. It took days of poor weather and low visibility before a plane could even get up there to look. That gap between the ground shaking and a human being actually laying eyes on what caused it is the single most important fact in this entire story, because it is the difference between an alert system and a coin flip. To understand why this kind of event is happening at all, and why scientists now believe it is happening more often, you have to understand what a glacier is actually doing to the rock around it while it's alive. A glacier isn't just decoration sitting in a valley. It is hundreds of feet of solid ice under enormous pressure, pressed directly against the rock walls on either side of it. It leans on that rock, and the rock leans back. For thousands of years, that mutual pressure is part of what keeps a fractured, glacially carved slope from simply collapsing under its own weight. Geologists call this buttressing, and it is exactly what it sounds like. The ice functions as a physical brace holding the mountain up. When a glacier thins and retreats, which is what has been happening across almost the entire Alaskan coast for decades as the climate warms, that brace disappears. What is left behind is a slope that has already been shattered and weakened by millennia of grinding ice, suddenly standing on its own for the first time since the last ice age, with nothing supporting it anymore. Two other factors are stacking on top of that thinning ice to make things worse. High up in these mountains, there is permafrost, ground that has stayed frozen year-round for thousands of years, and the ice locked inside the cracks of that frozen rock has been acting almost like glue, holding fractured blocks together. As permafrost thaws, that glue melts, and the joints it used to seal shut start to open. At the same time, Alaska has been getting measurably heavier rainfall in recent years, and that rain finds its way directly into those newly opened cracks. Water, sitting inside a rock fracture, does something mechanically brutal. It adds weight, it adds hydraulic pressure, and over repeated freeze-thaw cycles, it physically pries the rock apart from the inside. None of this is exotic science. It's the same basic physics as a backyard retaining wall failing after you remove its support and let water pool behind it, just scaled up to the size of a mountain. Layer all three factors together, thinning, glacial buttressing, thawing permafrost, and heavier rainfall, and you get a landscape across coastal Alaska that is more prime for sudden, catastrophic slope failure than it has been at any point in recorded history. To put the size of the Tracy Arm event in context, it helps to look at what came before it, because Alaska has an unusually long and violent history with this exact kind of disaster. The record for the highest tsunami run-up ever measured anywhere on Earth still belongs to a different Alaskan inlet, Lituya Bay, and it has stood since July 9th, 1958. That night, an earthquake estimated between magnitude 7, 8, and 8. 3 ruptured the Fairweather Fault in southeast Alaska. The shaking dislodged somewhere around 30 million cubic meters of rock from a cliff at the head of the bay, sending it crashing into a narrow inlet called Gilbert Inlet. The water there was driven up the opposite slope to a height of 524 meters, 1,719 feet, a number that remains, to this day, the tallest wave run-up ever documented in human history. 5 people died that night. 3 fishing boats had been anchored in the bay. 1 sank, taking 2 people down with it. Another boat was physically lifted and carried clear over the treetops on the spit at the mouth of the bay, and, almost unbelievably, the couple aboard survived to describe what had happened to them. Geologists studying the tree lines around Lituya Bay have since identified at least 4 other major wave events going back to the 1800s, which tells you this specific inlet has effectively been Megatsunami territory for at least 2 centuries. It is worth being precise about what that 1958 record, and the Tracy Arm number right behind it, actually measure, because it gets misreported constantly online. A run-up height is not the height of a wave, rolling across open water like something out of a disaster movie. It is the elevation the water reached as it was forced up the face of the opposite slope, measured afterward by researchers on the ground, tracing exactly where the stripped, scoured earth stops and untouched forest begins. Nobody watched a 1,700-foot wall of water sweep across Lituya Bay in one piece. What happened is that an enormous slug of water got shoved sideways with tremendous force, hit a wall of solid granite, and rode up it before falling back. That distinction doesn't make either event less lethal for anyone caught inside the inlet when it happens. If anything, it tells you precisely where the real danger is concentrated, close to the source, inside the fjord itself, in the first minutes. Tracy Arm is not even the only landslide-generated tsunami Alaska has produced in the last decade, and this is the part that should really change how you think about booking a glacier tour. In 2015, a large landslide in Fjord, in Icy Bay, generated a tsunami with a run-up directly across from the slide exceeding 620 feet. Just last summer, in August 2024, a landslide in a spot called Pedersen Lagoon produced a tsunami 56 feet high. Add those to Tracy Arm and to Lituya Bay, and you have 4 separate landslide tsunami events tied to the exact same underlying cause: thinning glaciers and destabilized slopes striking the Alaskan coast inside roughly a decade. Researchers studying the pattern describe a sharp uptick in these events over the last 10 to 15 years specifically, a tally of things that have already happened, not a theoretical projection. Which brings us to the slope that scientists actually are watching, and why the difference between watched and unwatched matters so much. About 30 miles from Whittier, a town with a year-round population of roughly 200 people that also happens to be the launch point for dozens of glacier tour operators, sits an inlet in Prince William Sound called Berry Arm. Above Berry Glacier, there's a section of unstable mountainside that geologists have simply named Landslide A. The U.S. Geological Survey estimates something like 455 million cubic meters of rock sitting at the glacier's front, with the entire unstable feature closer to 500 million cubic meters, roughly 650 million cubic yards. For scale, that is somewhere around 7 times larger than the entire mass that came down at Tracy Arm. Aerial photographs show this slope has been slowly moving since at least 1935, possibly as far back as 1913, but it only drew serious scientific attention in 2020, when satellite radar analysis flagged unusually rapid deformation. Between 2010 and 2013, the slope was creeping downhill at roughly 85 feet a year. That rate dropped to a little over 4 feet a year starting in 2017. Then, in August 2022, ground-based monitoring instruments picked up sudden acceleration between 41 and 69 millimeters of movement per day, 1.5 inches to nearly 3 inches every single day. Unlike Tracy Arm, Berry Arm has actual hardware watching it. Satellites pass overhead every few days, bouncing radar off the ground to detect movement down to a fraction of an inch without anyone setting foot on the slope, the exact technique that flagged the danger in the first place. On top of that, scientists have bolted GPS units directly into the rock, installed seismometers listening for the internal cracking of a slope beginning to fail, and placed cameras and water level sensors down in the fjord to detect the moment a wave leaves the shore, buying critical extra seconds even if the slope fails without warning. All of that feeds into a public alert level system maintained by the Alaska Division of Geological and Geophysical Surveys, a simple numbered scale anyone can check before heading out on the water, the same way you'd check a marine weather forecast. The early public estimate that circulated widely after 2020 suggested a full Barry Arm failure could send a 30-foot wave crashing into Whittier itself. That number has since been formally corrected by the same scientists who produced it, using an updated landslide tsunami model called DCLAW, published in U.S. Geological Survey Open File Report 2021-1071. Running 4 different failure scenarios, the model found that close to the slide itself, in the northern part of the fjord, waves could still reach roughly 200 meters, about 660 feet, essentially a repeat of the Tracy Arm and Lituya Bay numbers, and anything on the water up there would have almost no chance. But 500 meters offshore of Whittier, in Passage Canal, the modeled wave height dropped to just over 2 meters, roughly 7 feet, arriving at the town approximately 26 minutes after the slope begins to fail, with the first surge of energy reaching Whittier around the 20-minute mark. Jonathan Gott, who coordinates the U.S.G.S. Landslide Hazards Program, has said plainly that the original 30-foot estimate reflected a lot of early unknowns, and that new seafloor and landscape survey data gave researchers a far more accurate picture of what an actual failure would look like. 7 feet is still genuinely hazardous, especially for anyone in a small boat or standing on a dock when it hits, but it is an entirely different category of event than a 30-foot wave slamming directly into a populated town. As of the most recent public reporting, Barry Arm sits at alert level 1, the lowest rung on the scale, described as stable or moving only slowly, with deformation under 50 millimeters a day. Every monitoring instrument at the site is functioning and reporting data, with one notable exception, a water level sensor at Point Doran that has been offline. Nobody is on standby for evacuation, and there is no indication of imminent failure. But scientists studying this slope are remarkably candid about the limits of what monitoring can actually tell you. Geophysicist Jackie Kaplan Auerbach of Western Washington University has said landslides are notoriously difficult to anticipate. Dennis Staley at the U.S.G.S. has said it's genuinely hard to identify a specific trigger point in advance. And Brentwood Higman of Ground Truth Alaska, who has spent years studying exactly this kind of hazard, has said it's frustrating how much researchers still don't understand about how these systems behave. 3 separate scientists, 3 separate institutions, all landing on the same honest admission. Monitoring can tell you with confidence that a slope is moving. It cannot tell you what hour, or what day, or what year it finally lets go. That is the uncomfortable symmetry sitting underneath this entire story. The unwatched slope at Tracy Arm and the closely watched slope at Barry Arm ultimately end up in almost the exact same place, scientifically speaking. Neither one comes with a firm timeline. What the monitoring at Barry Arm actually buys, in the event of a failure, is not certainty. It's roughly 20 minutes of lead time, enough to sound an alarm, get boats away from the water, move people uphill before the first wave of energy arrives in town. Tracy Arm had 0 minutes of lead time. Everyone who avoided that fjord that Sunday morning avoided it purely by the accident of the clock, not because anyone told them to. If you have an Alaska cruise booked, or you're planning to book one, there are a few concrete things worth knowing. Every major cruise line that used to route through Tracy Arm has already pulled out of the fjord for the current season, redirecting instead to neighboring Endicott Arm and its Dawes Glacier, a route considered safer given the exposed, still unstable scar left above South Sawyer Glacier. Geologists say the area remains hazardous, with continued rockfall and smaller follow-on slides expected for years. If you're booking a smaller tour operator rather than a major cruise line, it's reasonable to ask directly whether they follow you. Hess Geological Survey and Alaska state advisories on landslide hazard zones and whether they've changed routes since August 2025. An operator who takes the risk seriously will have an immediate answer, the way the well-known 26 Glacier cruise out of Whittier reconfigured its route specifically to avoid the Barry Arm hazard zone. The Barry Arm alert level itself is public, updated by Alaska state geologists, and takes less than a minute to check before a trip, the same way you'd glance at a marine forecast. On the water itself, the response to a landslide tsunami is fundamentally different from what most people picture when they think of a tsunami warning. There is no 10-minute lead time, no rising siren, no gradual withdrawal of water off a beach the way you see with earthquake-generated waves in the Pacific. If you are in a small boat inside a fjord and you hear a sudden roar, or you see rock coming loose off a wall nearby, the guidance from people who study this is to move toward open, deep water and away from the shoreline immediately, because these waves are catastrophic against a wall and dramatically smaller once they spread into a wide, open channel. On shore, the instruction is even simpler. If the ground shakes or you hear that roar, you move uphill immediately, not along the beach, not toward your boat, straight up the slope, higher than feels necessary. The couple who survived being carried over the treetops at Lituya Bay in 1958 survived because their boat happened to be lifted over the spit rather than smashed into it. That was luck. Elevation, by contrast, is something you can actually choose for yourself in the moment. Here is where this story lands. The tallest wave ever recorded on this planet happened in 1958 in a bay where, by chance, only 3 small fishing boats and 5 people were near the water. 67 years later, the second tallest wave ever recorded happened in a fjord that draws roughly 500,000 boat-based visitors every single summer at 5:26 in the morning, an hour before the first tour boats of the day would have arrived at exactly that spot. The wave itself did not get any smaller between 1958 and 2025. If anything, the underlying mechanism causing these events, thinning glaciers, stripping away the rock support that used to hold these mountainsides in place, has only accelerated. What changed is the number of people standing in front of it every single season. Scientists are now watching Tracy Arm, refining their models, and building out warning systems specifically because they understand that the next Tracy Arm might not get the same lucky roll of the clock. Whether that warning arrives in time and whether anyone acts on it fast enough when it does is the question that is genuinely still open. For now, the safest thing anyone heading into an Alaskan fjord can do costs nothing. Check the alert level, ask your operator the hard question, and remember that here, the difference between a postcard and a headline can come down to a single hour on the clock.